Great. So I'm starting to record again. So just to backtrack a little bit, therefore. Very good. And thanks for reminding me about that. Right. So where we started, when we finished yesterday, we were speaking about the unregulated power supplies. And what we saw is that because it's a very basic design, some diodes, 1, 2, or 4 diodes, and a capacitor, and that is what is supplying a fluctuating DC voltage to a load, whatever that load happens to be. So there was the main issue with that is that first off, the output of the unregulated supply is not a flat DC. Okay, I'll just put a pointer here where we are. Right, so the unregulated supply does not provide a flat DC. There is a ripple. And the more current you ask the unregulated supply to provide, the more that ripple increases. And you can calculate the ripple from these two equations that we had here, depending on whether you're dealing with a half-wave, what do you call it, rectifier, which was this one here, or the full-wave rectifier. Now, the thing about it, well, I'll boil it down there. That little degree sign is supposed to be a delta. I don't know what happened there. As the current increases, delta V, which is the ripple on the voltage, increases. And if delta V increases, remember your average DC value given by this. Let me see if I can get this across here. Given by that equation here, the average DC value, if delta V increases, it means that the average DC value, which is the peak minus half of that ripple, is going to get less. So what we're going to have to do now is to find a way to stabilize that. The other thing is that if the line voltage changes, the output DC supply changes significantly. I mentioned that briefly yesterday, in that if, for instance, at some points, at some places in the country, the line voltage may be 122, 123 volts. In other places, it may be 115 volts. You design the thing and you have everything calculated, assuming a 115 volt supply, let's say, and you end up working it where the supply is actually 121, 122 volts. The DC output is going to be different than what you designed. So what we need to do is to find a way of putting some sort of other components or a system in place where we can minimize that effect. And that is what we call a voltage regulator. So we add another block onto the design called a regulation block. And now the end result is that we have a supply called a regulated power supply. And the function of that regulator is really to maintain a constant output voltage under conditions of changing load current and changing line voltages. Okay, so two things that you're trying to, that the regulator has to cope with. If the line voltage, the AC input to the transformer keeps going up and down or varying as the case may be, you want your voltage output of the regulator to be constant. And then if you take, within reason, if you take 1 milliamp or you take 1 amp from the power supply, whatever it's designed to do, if you take 1 milliamp or 1 amp at, for argument's sake, 12 volts, that the supply is going to remain at 12 volts regardless of what that current load was. Okay, now it seems challenging, but we're going to have a little look at that now and see in fairly straightforward terms how we can get around that. And the question too about the constant voltage. If you remember from your digital electronics, when you were doing digital electronics, there was a, just let me put this here a little bit. I don't know if you remember, back here a little bit, right? In your digital electronics, you remember when you were talking about when you were talking about voltage levels. So for instance, if you're talking about a 5 volt DC logic level, there was a voltage 5 volts and a short range below that is considered a 1 or plus, and then there's a voltage close to 0, somewhere between 0 and maybe 0.7, 0.8, or 1.2, depending on the particular device, that is considered a 0. Those depend very carefully on the device being powered with 5 volts exactly. There are also some devices that work with 3.3 volts. So it's important, if you are powering those devices with a power supply of any sort, if the power supply says it's a 5-volt power supply, it's supposed to remain to issue 5 volts to the circuits so that the logic levels could be interpreted properly. If instead of 5 volts it's giving you 4.5 volts, then what's going to happen when the circuit switches, it's not going to get into a voltage level that will be considered as a valid high, for instance, and you run into problems. Okay, so the whole idea of regulation is extremely important when it comes to powering devices like logic devices that require a certain voltage to be interpreted as a high. So there are 2 ways we can regulate the unregulated supply that we discussed before. One is by using a shunt regulator, and this is where the control element is in parallel with the load. In parallel, another electrical expression for being in parallel is shunting. So it's a parallel element. And then the other one is the series regulator, where the control element is in series with the load. The performance of them, we sort of classify how well regulators work by basically 3 factors: the ripple factor, the load regulation, and the line regulation. Okay, and these are, I mean, you could sort of figure it out. You don't have to remember the formula, but it's fairly easy to figure out. The ripple factor is the peak-to-peak ripple in the output voltage. Remember, the output voltage is going up and down a small amount, depending on how much current you're taking from the power supply. The peak-to-peak ripple divided by the average or the DC value of the output voltage. So it's a measure. So the more the thing ripples, the higher the ripple factor is. And your goal as a power supply designer or as a power supply manufacturer is to keep that ripple factor as low as possible. And for the same reason that we said before. So suppose you have a 5-volt power supply that has a ripple of 1 volt peak to peak in the output. That means that if it's 1 volt peak to peak, technically the output voltage could go up to 5.5 volts, or it could go down to 4.5 volts, right? That's a 1 volt peak to peak, from 4.5 to 5.5. At 4.5 volts, if it's working there, chances are you wouldn't be able to get the system to recognize a logic 1, because that may be 4.5 volts, may be too low for a particular device to recognize it. And 5.5, well, it will be, it probably work with 5.5, but certainly not at the lower end. And usually you get the peak-to-peak output ripple by putting an oscilloscope on the power supply. So once you have designed the power supply, you put it under the maximum load that the power supply is supposed to provide. So you connect it up to some resistors or something that is supposed to power. Load is you measure load by the amount of current that is drawn from the power supply. You maximize the load and you look on the scope to see what the ripple is. And of course, the oscilloscope has graduations on it, or the storage scopes will allow you to put a cursor so you can actually measure the values on the ripple. So you could get the peak-to-peak value and easily determine that. Yeah? Have you all used the scope as yet, by any chance? Anybody, when you were in the lab, were you able to use the scope at all?
Yes, sir, we use the scope.
Okay, so you understand, I mean, one of the things is that the scope to an electronics designer or an electrical engineer, a scope is like a stethoscope to a doctor. What you see with the waveforms, when you connect the scope properly, and the information that you get from looking at that is invaluable in determining many of the sort of parameters of a circuit. When it's if it's supposed to behave in a particular way and it isn't, the way you figure it out is to go in with a scope and actually look at what's happening at various points in it. So get very comfortable when we get a chance, of course, to get you back in the labs and so on. Make every opportunity count in terms of using the equipment and the scopes and the like especially. Right, so the other two things are the load and, oops, I have the wrong spelling here. That's supposed to be line regulation, right? So load and line regulation. So you can correct that. Yeah, right here. Okay. So the load and line regulation. The load regulation specifies how much the change in the DC output voltage from changing the load current. So it's kind of like the ripple, except that in this case, you're looking at the actual DC voltage. So you look at when there's no load, in other words, when the power supply is not supplying any current, and then you look at the DC load when the current, when the current is a maximum, and you divide that by the full load DC. And of course, you work it out as a percentage. And the line regulation is the change in DC output voltage resulting in a change in the input voltage. So for instance, if it's a measure of how good, you remember that thing we were saying that what we want to do is to prevent power supply input voltages from the line when the line fluctuates from varying the output. So what you do is that you change the input voltage and you look at the output voltage. So if you change the input voltage by 10 volts, you look and see what the output voltage has changed. And that gives you an idea of the line regulation. Okay? So again, all of these things in theory should be zero. But of course, we're dealing in the real world and we're dealing with the real world components and situations and so on. So it's not zero, but we try to get it down to things like less than 0.01% for good regulators. And it's fairly good. It's fairly easy to get it up to that sort of level. All right. So the regulator example is going to be the shunt regulator, and we use a Zener diode in that. The Zener diode is placed in parallel with the load. So this RL here, RL is representing the load. Now, again, just a little comment on the load. That load may be anything. It can be a DC operated resistor. It could be another computer. It could be another electronic board. It could be anything, right? The power supply doesn't care. What the power supply cares about is IL, the current. The power supply is designed to supply a particular amount of current. And that is what you want to make sure. So depending on what load it is, if it's supplying certain types of equipment, IL will be specified. If you try to supply more current than the power supply was designed to supply, then the power supply is going to fail on you. All right? So the input on this side, VI, on this side here, VI is coming from the diode capacitor circuitry that we discussed yesterday. So that is supplying the unregulated voltage and unregulated voltage VI to another little bit of circuits, a resistor, a Zener diode, and of course the load. Right? And you can recall, if you remember the Zener diode, a Zener diode works like a normal diode when it's forward bias. But we don't care about that. We have diodes to do that. The beauty of the Zener diode is when you reverse bias it. And what happens is that as you increase the voltage on the cathode of the Zener, as you increase the voltage on the cathode of the Zener, at some point in time, depending on how the Zener diode is made, the characteristic, if you watch the little diagram on the right-hand side of the screen, you keep increasing the voltage and nothing happens. And then all of a sudden at a particular value, the Zener starts to conduct. and it conducts and maintains a very constant voltage across the junctions of the Zener diode. The operator, well, of course, we operate that in the reverse bias, and it's called the breakdown region for the diode, but it's designed to work in that way. And there's another name for it that you may have come across, which is called the avalanche diode. And avalanches are sudden, there's sudden snowfalls that they get in the mountains and so on. It's the same thing. The current is going here, and then it suddenly avalanches in a way that keeps the voltage across the Zener diode constant. Now, there are two things you have to watch with the Zener diode, right? The current, I'll put this here. The minimum current and the maximum current that it can supply, right? Like all electronic devices, there are limits to them. If you ask it to supply more current than it has been designed to, it's going to fail. It's going to burn, right? The minimum current is the one where the Zener switch is on, right? So this point here, at this point, you have to supply the Zener with some current to get to that point. And then while you're there, you have to make sure that you keep that current below this other value here, right? So you operate it somewhere, and you want to operate it somewhere in this range here, which is where we have this here. So you check again. This thing that I always say, you go and you have to check the manufacturer specifications. What manufacturers will typically do is to give you a minimum, a typical, and a maximum. And you aim for the typical, all right? Go on here. Right, so here's what happens. As we know, we have the unregulated supply. We have the unregulated supply waveform, which is on the left-hand side there. The red voltage is what is coming into the regulator. And as we know, if you increase the load current, remember the load current is drawing straight from the unregulated supply. Forget the Zener for the time being. If I increase IL is going to be pulled straight from that unregulated supply, and the red line in the on the unregulated supply, which represents the ripple, is going to get wider and wider. And we know that. So at the time, when we put in the Zener diode now, when we add it into the circuit, the current that is coming from the unregulated supply has to supply both the Zener diode, IZ, and whatever is the maximum value of the load current. That is your specification, right? So you're given a task to design a power supply, so you know what IL max is going to be. The unregulated supply has to supply those two currents together. So therefore, if you juggle it around a little bit, the current, if you look at this resistor right here, let me circle it a little bit. If you look at the resistor right here, the current through that resistor is the difference in voltage between the lowest. Remember, the maximum load current gives the lowest value of V in minimum. So that's on this side of the resistor. And on this side of the resistor, we have VZ. So therefore, the current I is the difference in those two voltages divided by the resistance value. Yeah? And we also know from the little equation that went before, which is this one, we know what I is. We just calculated I. We know what IL max is. So therefore, we're now in a position to, because the Zener has to operate, whatever is the difference in those two currents has to go through the Zener to make it work. That is IZ min. So for this, the Zener diode to go, that current here typically has to be greater than IZ min. So we're now in a position to calculate what the resistance value is. the resistor has to be less than or equal to the difference in voltage divided by the sums of the currents flowing in the Zener and the maximum load. All right? Fair enough? Any questions? Feel again if things not clear at any point in time, stop me and ask the question, okay? Everybody following? I mean, it ties back to some stuff that I'm sure you did in the last year anyway. Okay, now, once that is set up here, if you decrease the load current, if you go on and pick another color here. If you decrease the load current here, remember the system is set up in such a way that it's a balance. You're supplying current, you have the current from the Zener, and you have the current on the load. If you decrease the load current, then because of how we've designed the circuit with this resistor, the extra current starts to go through the Zener diode. The power supply doesn't care one way or the other. It was designed to provide I. You calculated everything. I is a function of VI and VZ. VI and VZ. VZ is fixed. Yeah? VI was designed for based on what you made the unregulated supply to do. So if IL starts to decrease, what's going to happen, of course, VI, because you're taking less current from the power supply, VI goes up a little bit, but the extra current now is going to have to go through here. So on the other hand now, you have this limit now that you have to be aware of, that the current through the Zener now increases, and you have to be aware that when you reduce the load current, that the maximum current at that point in time never passes through the Zener. Okay? At least it doesn't pass through, it doesn't exceed the Zener carrying capacity. Fair enough? Let's see how that works. We'll run through a little example now and see how that works. So you're given something. You have an unregulated supply that varies between a minimum of 16 volts and a maximum of 20. So it has a ripple. It's going up and down. The peak-to-peak ripple is 4 volts. Using this unregulated supply, design a Zener regulated supply. So you're putting a regulator that is going to give me a nice 10 volts DC and be able to supply me with 10 milliamps. Right? So it's a 10 volt supply. 10 milliamps is probably charging, something very small, right? 10 volts, a little electronic circuit of some sort. So 10 milliamps is very small. Or it could be a battery charger, for instance, charging some batteries and that kind of thing. So the first thing is that we need to choose a 10 volt Zener for this circuit. So you get the 10 volt Zener, and then from that now, we have to calculate what is the value of the resistance to make the Zener function. Once you get the Zener diode, and we'll talk about that a little bit later on, you need to go to the data sheet for the diode. You have one presumably, and if not, you go online and you check the spec sheet for one that you have available, and you get whatever the minimum operating current, or as I mentioned, if not minimum, typical. Right? You could use minimum or you could use typical. You look and see what they give you. If they don't give you a minimum value and all they give you a typical, well, then that is what they're going to use. And we are assuming, just for calculation purposes, that this particular diode requires 5 milliamps to work. So you put it in here, and IL max is, from the design, 10 milliamps. Okay? That's what the current capacity of the power supply is. So once you do that, plug it in inside of here, you get that the resistor now is 400 ohms. The other thing that you have to look now, we have to go back through the diode, and we know that the diode first is a volt diode. That's fine, but how big of a diode? How much current is going to pass through this diode? And like resistors and other devices, they normally tell you they give you some specs on the diode, and one of the things they would tell you is the wattage rating of the diode. So the diode has a voltage, and the current rating through the particular diode as well will allow you to determine what is the sort of power dissipation going to pass through that. So if you know the power dissipation, then you can work backwards. Yeah. The maximum, and we just mentioned this, so the maximum current through the diode occurs when you remove the load, right? So when you remove the load, VI is a maximum, and all that current is now going to pass through D. So you're catering for when you have full load and when you have no load, essentially. When you do that now, the Zener diode current at that point at no load is the difference between here, the maximum, remember the power supply has a maximum voltage, it's going from a maximum of 20 to a minimum of 16. At 20 volts, you have 20 volts here. Keep having it upside down. You have 20 volts here. Okay. You have where are we? My arrow. Let me get my arrow again. Video, whatever it is. Give me a problem here. Okay. So the blue arrow, we have 20 volts. The red arrow, we have 10. So therefore, the current coming through here, remember we have taken the load out for this part, so there's no load anymore, so no current coming here. So you have a 10 volt difference across here, so this is going to send 25 milliamps, and the only place the 25 milliamps could go is through your diode. It's a 10 volt diode, so 25 milliamps passing through and a 10 volt drop across the diode means that the diode has to absorb at least quarter watt of electrical energy. It has to find a way of coping with that, right? It will get warm, it might do whatever it is. The usual way for electronic devices to handle current is by getting warm. So the diode will heat up, but it has to somehow get rid of a quarter watt. It doesn't sound like much, but when you remember that the actual PN junction is something microscopic, you're really asking it to contend with quite a bit. So if you're asking it to cope with a quarter watt, really and truly what we want is something with a little bit of a safety margin. So we're going to choose a half watt diode. Okay, 0.5 watt. So you now have your specs free for you. You go and you look now either in your electric stores like we do have here, or you go online if you're buying it, or you go to the nearest electronic stores. You go down to Shams Electronics up in the north here, and you tell them, now I want a 10 volt half watt Zener diode, and I want a 400 ohm, well, again, the same sort of thing, a 400 ohm half watt resistor, because I'm building up an unregulated power supply. Fair enough? Questions before we go to the comments? Yes, Sadie. All Goog. Okay, good. Yeah, what was the question? Somebody had a question. Oh, no questions. Okay, okay, good. All Goog. Very nice. Okay, so comments on the Zener regulator. First, they're useful for low power applications involving less than a few watts. All right, so again, if it's a very small circuit, sometimes, like for instance, those LED circuits that you see in, that they use in gardens, the garden light that are solar powered, right? So you have a solar power system is charging something, but the regulated circuit to provide the voltage for the LEDs may use something like a Zener regulator inside of it, just to keep the voltage constant so the light level doesn't fluctuate too much, right? You really want it under a few watts because the Zener must accommodate, when you remove the load, the Zener must accommodate whatever is the full load current being asked of it. Is the only thing in the circuit. Once the load is gone, what you have is a power supply connected directly to the Zener. So it has to be designed in such a way that it can handle that without an issue. Yes, Gian. Well, what's the question?
So now that you mentioned the solar, right? For independent solar system, normally you would have the charge controller series going to the battery. Would you consider that as a regulator, or it does the opposite?
No, a charge controller is a type of regulator. Absolutely, because what it's doing is controlling how much current goes into the battery pack. So that is a form of a regulation on the power supply.
Okay. Okay,
Yeah.
thanks.
And a very, on the expensive systems, it's a very carefully designed regulator as well. Yeah. All right. Okay. Right. So that's fine with the regulator, with the Xenon and so on. It works. It works for simple applications, and it's a very straightforward thing. So in some cases, as I say, if you have some simple applications, some very straightforward simple application, a Zener diode regulator may be all that you need. There are industrial power level Zener regulators as well. Okay, they use them in some sort of applications like industrial welding and in industrial motor control. And those actually are quite massive and they're capable of handling a few hundred watts. But they look nothing, excuse, they look nothing like the little devices, like the little small signal diodes and so on that you're accustomed seeing. These are devices that look like a small, like a very small can of paint with heavy duty cabling coming in and out. All right, and in those cases, they are deliberately designed to pack, to carry a lot of energy and to dissipate a lot of energy, but they have to be mounted in a very different way as well. Okay, so for our purposes and for handle, what shall I say, simple electronics and the low power electronics that we deal with, right? That's the key, that the Zener will be fairly small. But they are, in just to be aware that there are industrial applications with very high powered devices as well. Yeah. Okay, so let's just look at something else here, just a little bit of some extra discussion. When the diode is operating, it actually has a resistance when it's conducting. Okay, they call it a dynamic resistance. It's not a perfect device as you would expect. So when it's on, there is a resistance through the PN junction. And again, depending on the type of diode, it can range from 5 to 100. This is supposed to be ohms here again. All right, take this out. Right, ohms. Yes, Kamaraj. Question?
So, you can
Yeah.
remind me what will be the voltage when a Zener diode is operating in forward bias and reverse bias?
Yeah, the forward bias, just now, the forward biased, right? When the diode is operating in a forward bias mode, a Zener operates pretty much like a regular, what do you call it? A regular small signal diode, a normal PN diode. So the forward voltage drop across it will be in the vicinity of 0.7 volts to maybe about 1.4, 1.5 volts. Okay, the forward voltage drop is a little bit more than a normal diode because of how the PN junctions are doped in the Zener diode. It's different from, like, let's say, a rectifier diode, for argument's sake. So, but when it's forward bias, it works just like a normal forward bias diode, and it drops somewhere between 0.7 and maybe about 1.4, 1.5 volts. The spec sheet will tell you that. When it's reverse bias is when it behaves like the Zener that we know, right? So once you start to reverse bias it, as soon as you cross the current rating of the diode to turn on in the reverse bias region, the diode, the PN junction breaks down and maintains the Zener voltage across the junction once you operate it within the specs. Yeah? That answers the question? Nice. Okay, yeah. So no, I think in your handout you have it correctly. This is just when it gets translated for Blackboard, it seems to ignore certain symbols here all the time. So the dynamic resistance of the diode when it's conducting, and this is conducting, it's reverse bias. So the diode is operating as a Zener. When it's working as a Zener, it has a resistance when on of somewhere between 5 and about 100 ohms. I guess you have to check, again, you have to check the specification sheets to see what happens. Now that load appears in parallel, resistance appears in parallel with the load. So just a little bit of simple circuit theory here. When the diode is operating from a resistance point of view, this is the circuit that we have here. We have the Zener here in parallel with the load resistance. Okay? Now the Zener diode, we just said, this is somewhere about 5 to 100 ohms. Let's say 5 ohms. And you know from a simple circuit theory, if you parallel two resistors, if one is much bigger than the other, then the net result of the parallel combination of these two is always going to be smaller than the smallest value. All right? So what's going to happen inside of here is that first off, if you do the simple circuit theory, you see that the output voltage VR over the input voltage is a simple voltage divider. RD in parallel with RL, so that the current through will be the voltage VR will be divided according to RD in parallel with RL over R plus RD in parallel with RL. Yeah, normal voltage divider behavior, except that these two resistors are in parallel. We know RD is small. We know RD typically is going to be much less than your load. So if that is the case, then VR over Vin depends on this value of RD here. Okay? If that is 5 ohms, if that is about 5 ohms, then we have to make sure that the load resistor that we are supplying, whatever this is going to be, whatever we're designing this to do, is much greater than that. And you're talking about at least 10 times greater. Okay? So if you have a diode and the diode happens to be, the on resistance is 100 ohms for argument's sake, then your load probably has to be somewhere in the region of 1,000 ohms or 5,000 ohms, that kind of thing, something considerably more. All right? And that's just electronic design. And this is where the whole thing about loading comes in. Because many times you would find that students, for instance, would come into the lab, they design a circuit, and then after they design the circuit, they implement it, and then when they hook it up to power, for instance, whatever it is, they design the circuit, you design the power supply, when you hook up the power supply to the circuit, nothing works. And your sort of automatic belief is that something was wrong with the circuit. One of the first things you check when things don't work is to go back to the power supply. Am I getting the power that I need? And that is the case here, that if you did up a design and then it turned out that, let's say, okay, the diode that you're using had on resistance of 5 ohms, which means that the load probably shouldn't be less than 50, and the load turns out to be at a 10 ohm load that you put it on, then the diode regulator is not going to supply the voltage that you need. All right, and the system wouldn't function. You try to turn on the electronics and it doesn't work. Okay, so there are things that go back and forth a little bit, and you must always remember that. Right, always remember there's a reason that we're talking about these things. There are reasons that manufacturers give you data like the diode on resistance. Why? Because it determines what you could put the diode regulator on. They give you things like a power dissipation. Why? Because it determines how much current they can pass through the Zener diode without burning it. In the case of the capacitor, the working voltage. How much voltage can I put before the capacitor fails? In the case of the rectifier diodes, the PIV value in when how much reverse bias or how much inverse voltage can I put on the diode before it will fail. And the normal resistors that you have, the resistors are quarter watt resistors, half watt, 1 watt, and so on. The wattage rating tells you it's passing current. Remember, you pass current through a resistor, it's going to dissipate heat at I squared R. And that, I mean, it has to dissipate. It has to get, once it's passing current, it has to dissipate the heat. It doesn't have a choice. And in dissipating the heat now, if you put a quarter watt resistor, can it dissipate? Are you asking it to pass more heat than that? If not, it's going to get hot and it's going to be destroyed. So all of those things go into the mix, right? And you must always be careful when you're designing and when you're discussing things from an electronic basis or from any engineering basis, why you are doing something. Yeah? Fair enough? Questions? Yes, Jamal, question. Is that a question or everything is all right? Right, so great recap 10, 11. There we go. So, as we said, someone's saying something?
So, yeah, excuse me. So,
Yeah.
Basically, when I was reviewing it, basically we're saying sometimes if a safety precaution is if the Zener diode starts to get too hot, all we really need to do is get a Zener diode with a higher current rating.
Right, but here's the thing. You don't want to be in this situation where you design the circuit and the Zener diode starting to get hot and say, oh, you know, wow. Take out the diode and put a bigger one. You want to do that up front.
Yeah,
okay?
Okay, true.
Right? Just think about it. I mean, let's say you there and you make a power supply for a friend to do something and they take the power supply and they go home. Or you make something and they go home and the thing starts to get hot. No, it's in a case and it's sealed up and it's getting hot. You can't tell them, hey, okay, let me swap that Zener for a bigger diode, for a bigger wattage.
So that's why when I was doing the calculations, right, and the Zener current, it came up to 0.25. For safety, you said you said to do a half watt for safety.
Absolutely. We mentioned that yesterday with the transformer as well too, and the capacitor as well, that you always give a safety margin. All right. Once you design a specification, that's the exact design. So you always the power ratings. The only thing they really can't change are the actual resistor values, but you can't change the wattages of the resistors and so on. Right. The things that bias the circuit and the voltages and currents that make the circuit work, you can't change. But what you can change are the power rating of the components to make sure that they can handle what you're asking them to do. All right, and again, somebody asked that yesterday about the manufacturing of, for instance, the capacitors, and if all of them are made the same way. So this would be a case in point: a cheap circuit that is designed to mass produce and be made by the hundreds of thousands. For instance, let's say you're making something to go into a simple toy, right? Something that is sealed to make some noise for a little while and then that throw away. Right, you would probably go as close to the design limit as you can, because it will be clearly in our case a half watt Zener will cost a little more than a quarter watt unit. But if the end product is only designed to last a few months and it's going to be thrown away anyway at some point in time, you would probably go for the cheaper option because it's the cost savings and the whole economics of it doesn't make sense to go for the better one. But if you're designing something to work in a lab, or you're designing something that has a more critical application, right, controlling something or measuring something, or in health or aerospace or something of that nature, then obviously you want the safety margins in there. Okay, so it's all a trade-off. That's one of the things you will sort of pick up as you go through in engineering. We do a lot of design and analysis, and the final products, you always have to trade one thing against the other, right? A lot of time, economics and money and time have to be balanced against the cost of the components and the reliability. All right. So people, for instance, we have an engineering team in UE that have manufactured a prototype ventilator to work with the COVID patients. The situation was that if things really got bad, ventilators are the things that keep people alive, and there's a very limited supply of them in the country, and there's and worldwide because of this thing. So the UE design team and there were people from the Department of Electrical Engineering, Electrical and Computer Engineering on that. There is a prototype design that they have, and it could be manufactured very quickly if the demand for it exists. But the thing about it, that's a medical device, and the sort of care and the type of components that they use for that would be extremely reliable components, and there were standards that they had to meet for that. So you would have things that could switch on and off 50,000 times before it fails, or things that could go on and off 100,000 times, or something that could remain in constant operation for 5,000 hours without turning off. Those kind of things, and that's certainly different from an application where you wanted to design an electric fan to keep you cool, right? A DC powered electric fan, certainly you wouldn't want that kind of thing. All right. So it's a lot of words just to say that what we do in engineering is always a trade-off. And the important thing to learn, somebody once told me, is that it's important to learn what the rules are before you try to break the rules. Okay, so always learn the standards, always learn the requirements, and in our case, what is the correct design, what are the correct specifications, and then once you have that down, then you can see how you want to modify it after. Yeah? No shortcuts. People get hurt because of shortcuts, and in electrical engineering, you know that it doesn't take too much current to kill or to injure, right? Especially alternating current. So mistakes and carelessness and poor designs can cost not only money, but it can cost in terms of injury and lives. Yeah. So always keep that in the back of your mind. It doesn't take much to injure at all, not at all. Okay, so let's look at this little modification here now. The Zener diode is all great. It works up to a point, but the failing of it is that it doesn't supply that much current. If the load is removed, then the Zener has to cope with that difference, so that there's a sort of a tight zone between the minimum and the maximum. The Zener is to put another component that sort of takes away the work of the Zener. In other words, let the Zener do what the Zener does well, which is to provide a constant voltage. And let this other device now take the current handling part of it. And that's where we put in what we have here, right? Where we put in what is known as a pass transistor, PASS, a pass transistor added to the Zener regulator. And what happens now is that at this point in time, all the Zener, the only load that the Zener is seeing is the base current for the transistor. The transistor is what is actually supplying the load current. So the unregulated supply, again, is supplying the load current as it was designed to do. The Zener is just simply taking, let me get another color here. The Zener is taking its own current just to keep itself operating. All right, whatever is that thing, and you get that from the data sheet. And the transistor now is taking all of the the current load. The Zener just has to provide now whatever bias supply is needed by the transistor. So let's see how to design with that now. Right? A little thing to note, notice that the output voltage, we are using an NPN transistor here. The output voltage, there's a positive voltage going here. So that the output voltage, the Zener diode, is whatever is our output voltage plus a 0.7 from the forward biased base emitter junction here. Okay? And then the other little thing to remember is that the base current of the transistor, whatever the collector current is, the current gain of the transistor, your HFE times IB. So that's going to figure into this as we go forward. So here's it. Let's work through the process again. So we have a Zener diode capable of delivering 12 volts at 100 milliamps. So design a regulator now. Design a single transistor regulated supply using a Zener diode, and the power supply is capable of delivering 12 volts at 100 milliamps. And we're going to use a half-wave rectifier, and that's just to make the problem a little more interesting. All right. So you go up here. The first thing now is the actual value of the Zener. And this is where those choices that we keep getting presented with, another one comes about. If we want 12 volts on the output, because of the 0.7 volts here, the Zener is actually going to give you you actually need a 12.7 volt Zener. If you go on a site like DigiKey, and I have this site here on this slide, just in bold for you. If you go on DigiKey, and they have components by the thousands, all kinds, and you look for Zener diodes, you're going to see all kind of voltages, but you're not going to see 12.7 or anywhere close to 12.7 in a usable device. The closest usable one you're going to get is 13 volts. And I picked up one, I mean, just out of it, there's a picture of it on the screen. 13 volt is manufactured by a company called Vishai. It's a 13 volt Zener diode there, right? Okay, just a second, excuse me for a second, I have to take a call. Hi, yeah, sorry about that. Right, so you went there, and I went onto the site, and there's a 13 volt Zener. There's a picture on the screen next to the circuit diagram, what it looks like. So that now changes the issue a little bit. So we really need the design, the specification told us 12 volts, and to use that, we're supposed to use a 12.7 volt. So we actually, but you can't get that. The design is going to use 13 volts. So that's part one. The second part now is that we have the transistor in the circuit here. For the transistor to operate, you typically need the collector voltage to be more than the emitter voltage by about 3 volts to have proper conduction through the transistor. It's just a guide, and you could go back to your transistor notes. Again, sometimes transistors will vary depending on the power rating of the transistor as well. So let's say we need 3 volts more, 3 volts across the collector to emitter of the transistor for it to work well. The input is a 15 volt. If we want 12 volts coming out, the input is supposed to be about 3 volts more than that. So that we want here at least the average value of that to be about 15 volts. And if the average value here is coming in, then if we use, like for instance, a 15 volt transformer, therefore, if you have 15 volts here, remember last time we said, okay, you have 115 volts DC, you pick a 15 volts transformer, and that's going to pick us, give us about a peak voltage of about 21 volts DC coming in on the rectified side, right? So just to put the diagram on top here, this is what the thing is going to be. Unregulated, now we're going to have about 21 volts coming in here, all right? We could now decide how much of a ripple you want in the unregulated supply, which is back to what we did yesterday. The more ripple you can tolerate, the smaller the capacitor that you're going to need. If we pick a relatively small ripple, which is 1 volt plus or minus, so it's going here, so you want the peak to peak to be 1 volt, meaning that the unregulated supply could go between 21 volts peak, and then it could drop down to 20 if there's a 1 volt ripple. Not bad. Okay, if you calculate the capacitor value, then you're going to get another thing. Again, this is micro here, please. If you calculate using the little equations that we developed yesterday, you're going to get that the filter capacitor for the unregulated section is 1667 microfarads. You're not going to get that. If you check up the standard capacitor values, and I'll put up a little table that I have, I was supposed to upload it for you. You're going to find that the closest available commercial value to 1667 is in fact 2200. So 2200 microfarad, and the working voltage here, seeing that we're working at about 20, we're asking the peak, the system to cater for a peak voltage of about 21 volts DC, then I would probably go for a 35 volt capacitor. The next closest one would have been 25 volts, but it's a little small, so I would probably go for 35. Okay, that's the next one up there. You wouldn't get a 30. So you have that, and we put that, let me just back that. So we have the 13 volts Zener into the system here. Let's put some other values now on top of here. If you look at the diagram, the circuit diagram, the Zener, right, the Zener is 13 volts. Because of the voltage drop on required to bias the transistor, our output is actually 12.3. Remember, the design was asking for 12, but we're actually getting 12.3. Okay, let's calculate the resistance for the Zener. The peak DC is going to be 21 volts, which is what we have up here in the diagram above, the little current, the little waveform above. If the peak is 21 volts, the Zener, according to the spec sheet for that device that I downloaded from DigiKey, the Zener requires 5 milliamps to operate. It is a 13 volt Zener, so the current through that resistor is 1.6K. All right, so that we now have that value in here. We have 1.6K, we have the 13 volt Zener. We now have to look at the transistor itself. What kind of transistor do we need? On the other side now, when we're going at maximum current is when the voltage of the unregulated supply drops to its minimum. At no voltage, at minimum current is at 21. And you remember we designed it in such a way because we said it's a 1 volt ripple, so that at maximum it's going to drop to 20 at full load. All right. So at full load, the collector of the transistor has 20 volts. The emitter of the transistor has 12.3 volts because it's a 13 volt Zener that we're using. So that the power dissipation, remember the power supply is designed to carry 100 milliamps. So if the voltage across the transistor now is 7.7 volts, the difference, and the current through the transistor is 100 milliamps, the transistor is going to be asked to dissipate 0.77 watts, about 3/4 watts. So again, safety margin is not that much. Let's see what we have in 1 watt transistors. And again, if you go onto the DigiKey, same DigiKey website, a manufacturer called On Semiconductor, they make a lot of these diodes and transistors and so on. They have a particular transistor that is a 1 watt transistor that can handle this sort of current. You go and you check the spec sheets, of course. Right? This is what the transistor looks like, a normal small signal transistor. And the transistor is something called a TO92 pack. Okay, that particular type of case is something called a TO92 pack. And we'll talk a little bit about cases as we go through the discussion here. If you look at the data sheet for the transistor, it tells you that the transistor has an HFE of 100. So if it has 100, it means that the base current, remember the power supply, the collector current, or the current through the emitter actually, which is passing through the collector, is 100 milliamps. So if it's passing through 100 milliamps here, then the current through the base of the transistor is that divided by HFE, which is 1 milliamp. So the Zener only has to supply a total of 1 milliamp. All right. So before I go on, that's your final design here. So you were asked to design a 12-volt supply to give you 100 milliamps. With everything and what is actually available to you, you're able to give 12.3 volts at the 100 milliamps. You have a transistor that is able to dissipate the power required by supplying that. The Zener diode doesn't have to dissipate any kind of power because the Zener diode is just operating at its own bias current, which is 5 milliamps. And all it has to do is, of that 5 milliamps, an extra 1 milliamp to bias the transistor and to keep it operating. So questions? Any comments? Right, how did you get 20 volts and not 15 volts? Right, 20 volts and not 15 volts, where were we? Right, so what we was, it turned out that way because when we went back, this is where things suddenly sometimes change for you, right, okay. If we want, remember how it started? We were saying we wanted 12 volts here. If we want 12 volts here, then we need 15 volts here. If we need 15 volts DC, what we said for the transistor, remember yesterday for the unregulated transistor, for the unregulated power supply, sorry, if we need 15 volts DC, we said that, okay, we could probably use a transformer with a 15 volt secondary, which, so 15 volt secondary means that we could get up to a peak of 21 volts. So although we said we need at least 15, we actually working with 21, right? The 15 root 2. Okay, the thing you could use now, there's the thing, if I use a 12 volt transformer instead, what would be the peak voltage for the 12 volt transformer? Right, from what we did yesterday, the peak voltage of the 12 volt transformer would be about 17 volts, 16.9 something. So in theory, we could use a 12 volt transformer and have 16.9 volts here, 17, and work and design the circuit around that. Absolutely nothing wrong with that. Okay, there's absolutely nothing wrong with that. And that is a kind of, I mean, it's an interesting decision. So if I were to give you this and somebody said, okay, 15 volts DC, instead of using, I could go backwards. So if 15 volts is the sort of peak that I want, I could work out what the equivalent RMS is and give myself a little bit extra. And if you were to tell me, okay, I will use a 12 volt transformer, which is giving me 16 volts coming out here instead, I would agree with that because you're at least more than the 3 volts across the transistor for it to operate. So I have no problem with that. If you were to go with less, like a 10 volt transformer or something like that, then you run into problems. Here we just follow the rule of thumb. You want 15 volts, at least for low voltage values, you want 15 volts DC. A 15-volt transformer will give me enough headroom up to 21 volts to comfortably supply that 15 volts DC, should anything arise. But there's nothing wrong with being a little more, a little tighter if you want, bearing in mind what you might actually get to buy. Yeah? And, okay, so any other questions on that? Yes, Joshua. Joshua? You're typing or you're talking? Not coming through. What? Okay, so what isn't coming through? So type what you want. Right, what was the frequency used when calculating the filter size? I'm assuming 60 hertz. Okay. If you're in another part of the world, Barbados I think has 50 hertz, or Europe has 50 hertz. Europe, for instance, is a 240 volt 50 hertz supply. The UK is like that. The US is like us, 60 hertz. Some parts of South America are 50 hertz. I think Barbados is 50 hertz. So it varies. I will assume for our purposes, and all the way through, I will assume 60 hertz, because that's what we normally deal with here. All right. Any other questions? Okay, so some comments on this now. First off, of course, we didn't get 12 volts. Somebody asked us for 12 volts, we give them 12.3, which may be a problem, right? For instance, those electronic devices, the microprocessors and logic devices that work with 3.3 volts. If somebody came to you and told you, I needed to design a 3.3 volt supply for me to power some digital electronics, and you come back and say, all right, well, I did it, but they're giving 3.3 volts. It's actually giving me 3.6, right, or 4. You're going to run into problems there, okay, because the 3.3 volt devices cannot work with more than 3.3 volts, right? So the first thing is that if you have a spec, you want to really get the spec around. The regulation is okay, right? It's better than the shunt regulator, but it could be improved, and we'll talk about that upcoming. And then some other things happening right now. What happens, for instance, if I short circuit? If, for instance, the load resistor here, if, let's say, you were connecting that up and you were connecting it on a breadboard, for argument's sake, and you accidentally shorted the power supply, what would happen? Right, at this point in time, what's going to happen is that the supply is going to go directly to ground. If you short circuit, then the load current goes up drastically, right? In theory, it's going to go to infinity. Of course, the system can handle that, so it's going to handle the maximum capability that the device can handle, the devices can handle. This transistor, you go back to the data sheet, it's a 1 watt job. So if it is a 1 watt device, we already have 7 volts, approximately 7 volts across it by 1 watt. You know how much current it could handle, right? You just divide the wattage by the voltage. So the instant that current passes that load, this transistor is going to burn. And if the transistor burns, well, the power supply fails. If the transistor doesn't burn first, then remember the current is coming from your diode, your rectifiers, and the capacitor. So if the current overloads the diode and the capacitor, somebody is going to blow before the thing eventually shuts down. So you always have to cater for that kind of thing. What happens for short circuits? So let's look a little bit now just at a block diagram. And after the discussion, we'll end here and continue it next time. Right? Here is a little modification of what we have there, and it is called a series feedback voltage regulator. In already labeled, what we just did was we have this Zener in blue, we have this the reference already. So we have this part available for us, and we have this bit available for us. What we're now going to do is to add the part in the red dotted box. That is new. And look at what's happening inside of here. We're going to add some circuits or a circuit. And the circuit now is going to basically compare what is coming out, that whatever design voltage that we have, against what is supposed to be coming in. Notice part of it, one signal is coming from the output, right? So it's there. This is a voltage divider. So whatever the output is, we divide it, and we're taking that and we're sending it to a circuit. So it's taking part of that. It's actually sensing that, but sensing that voltage by taking a fraction of it because of this little voltage divider. So something is coming in inside of here. And then from the reference voltage, which is our Zener diode in this case, we're putting in a value here. So the Zener voltage goes in here, and some fraction of the output voltage comes inside of here. This amplifier now is going to send a signal to the series element, which is our pass transistor. So that if this varies at any point in time, just now, excuse me a second. Yes, apologies again. So if whatever, we have this Zener voltage and we have this sensing voltage coming in here, this little circuit here is going to send a signal to the series element, so that if this voltage output here varies, for instance, the load changes or the load shorts out, what is going in inside of here in the error amplifier is going to stop the signal going to the series element and shut it down. Or if this voltage, for instance, gets too low, then the error voltage is going to increase the current drive to the series pass transistor to make it pass more current and get the voltage back up. And similarly, if it goes too high, it's picking up that, and it's going to reduce the drive to the pass transistor and get the voltage coming down. So it's trying its best to limit. Okay, this is called a series feedback voltage regulator. A series regulator is what we're talking about. The feedback, because we're taking something from the output, measuring it, and sending it back into the system to do some control. So the next time around, we're going to actually look at the circuit that does that, that creates this error voltage behavior for us, and analyze it and see where we go from there. All right?
Excuse me, sir.
Yeah.
Can you repeat what the purpose of the reference voltage was again?
Right, the reference voltage. This is our Zener reference. Remember, once you are designing a voltage regulator, you must have some reference voltage around to work with. The only way you can know if there's if a voltage regulator is supplying some design voltage value is if you have a reference. It must be able to work with some, it has to have a standard to go by. That standard is coming from, in our case, the reference voltage is going to be a Zener diode. Right, remember the Zener diode creates a fixed voltage once it's biased properly. So that is our reference. If I want a 12 volt out, I'm going to put a 12 volt reference here or something of the nature like that, right?
Okay. Understood.
Nice. Yeah. And this amplifier now is going to compare what, in other words, in plain English, the error voltage amplifier or that circuit compares what I want with what is really happening and tries to correct it. So if what is really happening is equal to what I want, the error amplifier does nothing. If what I want is different from what what I'm expected to do, the error amplifier will take some corrective action to adjust as required. Yeah. So next time we're going to spend some time, and that's the other discussion on this now. How do we put in that error amplifier inside of there? And there are two ways to do it. One of them involves using an operational amplifier, and the other one a simple transistor. And we're going to have a look at all of them, and then tie it up with things like short circuit protection and overcurrent protection as well. So you're going to finish off the next time we meet, we're going to complete the power supply design with all of the elements that we need. Okay? So any questions at this point in time? Everybody all right? Yes, Jamar.
Sir, I just have a small question. On the voltage ripple or the ripple, I think it was on page 20.
Mm-hmm.
You said that the reason why that the voltage peak starts off at 21 and then heads down to 20. Could you explain that once again for me, please?
Okay. You remember when we were talking about the unregulated supply yesterday, right? The unregulated supply, there is a ripple on the unregulated supply because once it's supplying current, remember the only quote unquote device in the unregulated supply that is sort of trying to keep the voltage constant is a capacitor. Once you start to pull voltage from the power supply, the voltage from the unregulated supply now starts to fluctuate. It starts at some value, which is a peak value. The capacitor charges up to the peak value of the rectified output, whatever that value is. But it discharges because you're asking the capacitor to supply the load. So the capacitor will discharge until the next charge cycle comes around, and then it will charge back up quickly to V peak again, and then discharge. Yeah. For what we were saying, in our case, we're using a 15-volt transformer. So a 15-volt transformer means that the peak DC that you're going to get out of that is going to be 21 volts. And we also said here that we're going to choose a ripple voltage of 1 volt. So if the peak voltage is 21 volts and the ripple voltage is 1 volt, it means that at the end of the day, the voltage can go from 21 high to 20 low. All right? And that's where those two values came from.
Okay, thank you, sir.
Right, that clears it up?
Yes, it does.
Okay, great. So any other questions? Okay, well, if not, I'll draw the session to a close. Is the charge cycle like the rate of the clock? The charge cycle is the frequency of the signal coming in, which is 60 hertz. Yeah? Just go back over the slides from yesterday, and if anything, you will let me know. Yes, Jamal?
Oh, I'm sorry, I forgot to update on my.
Okay, no problem. Yeah, somebody was saying that they're trying to make a connection between what we learn in labs and what? What you learn in lab, what is the connection that you're trying to make? Yeah, no. The clock, a clock, yes, a clock is a signal. A clock is what you use for instance, in digital systems, the clock is where the system changes. Every time the clock goes from low to high, the logic in sequential systems will change. Or in a microprocessor, it uses the clock as a timing mechanism. So things have to happen every time the clock changes, either the rising edge or the level. Our charge cycle here, remember what the capacitor is charging and discharging because of the wall voltage, which is a 60 hertz signal or a 50 hertz signal. So it charges every 60. In the case of the half-wave rectifier, it charges every 1/60th of a second. Or in the case of the full wave, it charges every 1/20th of a second because it's twice as fast. Yeah? Make sense? All right. Okay, so at this point in time, so I'll draw today's session to a close. And next week, Monday, please God, we will take up this whole question of the error amplifier and the series feedback and close off the discussions that we have on the power supply. Yeah? So everybody, thanks for attending, and I'll see some of you all again right after lunch. Take care.